Our group's project is the Fibonacci sequence in relation to linear algebra. The Fibonacci sequence is a series of numbers in which each number is the sum of the two preceding numbers. These numbers are called the Fibonacci number, and the sequence starts with two ones. As you can see from the image there, it shows the first few terms of the Fibonacci sequence.
So as you all know, one easy way to find a term in the Fibonacci sequence is to use the recursive formula, which requires the knowledge of the previous two terms. And the formula basically looks like the following, written in blue: an equals an minus 2 plus an minus 1, which is basically adding the previous two terms to generate the next term. To connect this with linear algebra, we brought a question from the textbook, which is shown in the left side of the slide, which asks, explain how the matrix identity given can be used to generate the Fibonacci sequence recursively. So basically, the product of the matrices will return the nth term and the n minus 1 term. So substituting the matrix that was originally multiplied by the 1, 1, 1, 0 matrix for the result matrix can give us the n plus 1 term, and can generate every term after that if you keep multiplying it. Just how we know that the recursive formula requires the previous two terms, this would be troublesome when we don't know the previous two values. And so to take a step further, we wanted to use eigenvalues and eigenvectors to find the explicit formula for any term of the Fibonacci sequence. And to review what the explicit formula is, what an explicit formula is, it's basically a formula that allows us to simply plug in the value of whatever term you want for n, and then we can easily find the nth term of the Fibonacci, or we can find the nth term of any sequence or any formula, but in this case it would be the Fibonacci sequence. And the formula looks like the following on the bottom right corner of slide 3. And basically, this whole project will show you how we will explain how we can use linear algebra to find this explicit formula. So going on to the next slide, we will start with step 1, which is defining x. We will define xn minus 1, where xn and xn minus 1 represents the n and n minus 1 terms of the Fibonacci sequence. So to show it to you in a more visual manner, writing out more x terms would look something like this. So n equals 1, the first term would be the matrix 1, 0, and the second term would be the matrix 1, 1. The third term would be matrix 2, 1. The fourth term would be the matrix 3, 2, and so on. And all these vectors are defined in this space R squared.
So by utilizing this 2 by 2 matrix A, we can multiply two consecutive terms of the Fibonacci sequence by A to find the next two terms of the Fibonacci sequence. And this is essentially a recursive rule for the Fibonacci sequence, but written in matrix form. So what we can actually do with this information is that we can start with the first two terms of the Fibonacci sequence, which are 1 and 1, and then we can multiply by A repeatedly n minus 2 times to find the nth and n minus 1 term of the Fibonacci sequence. So the next step is to actually find the eigenvalues of this matrix A. The reason we do this is because we can't exactly write an expression for A raised to a certain power, as we did in the last step. We aren't able to actually write an expression for that would allow us to find the explicit rule. So we want to find the eigenvalues and eigenvectors in order to find a matrix P that can diagonalize A, in order to find a different way in which we can write A. So as you can see, we found the eigenvectors, eigenvalues, and then found the matrix P, as well as the matrix D, which is the diagonalized form. And then so we combined step 2 and 3 in order to derive the explicit formula for the Fibonacci sequence. So essentially we replace a to the n minus 2 power with p d to the n minus 2 power times p inverse. And then we multiply out and simplify to find the explicit formula.
As you can see, this is the explicit formula for the Fibonacci sequence. Fun fact, the eigenvalue 1 plus root 5 over 2 is actually the golden ratio 1.618, often denoted by phi. This can be found by dividing one term of the Fibonacci sequence by the previous term, and eventually the result will converge to the golden ratio.
Here are the links to the resources we used in this project, and thank you so much for watching.